And this is also something about hybrid orbital, and they wanted to something have a better understanding, just sp, sp2, sp3, and so on. And this is an example. And this is a compound. Hydrocarbon means make up with carbons and hydrogens. And this is called the butadiene. You know, butadiene, butane means how many carbons? 4 carbons. You know, diene means 2 ene, right? So it has a 4 carbon with a 2 double bonds. So you draw 4 carbons with double bonds, and they kind of alternate this way. So that's sort of the basic skeleton, and the rest of them is essentially carbon and hydrogen. So it should be looks like this, and this is what you see in the bottom. And the one in the bottom is, this one is better than the one in here because I mislead you by having this bond is flat. It's not. It is always a triangle planar structure for sp3 carbons. So this is a carbon, those all 4 carbons, what kind of hybrid orbital those carbons have? The answer is sp2 hybridization. So that's an entry-level question. But now the question involved in something a little bit more than that. So they tried to explain it to you. If you're looking at the double bond, carbon length is 134 picometer, whereas a single bond, which is between 2 and 3 carbons, 147 picometers, which is shorter than the normal carbon-carbon single bond. So the key one is actually this one. The normal single bond length is 154 picometer. Okay. By the way, do you know what picometer means? 10 to the minus 12, right? You know the nanometer? Negative 9 meters. Do you know what angstrom is? What? 10 to the negative 10 meters. So why am I saying this is, actually I can write this 154 picometer or 0.154 nanometer or 1.54 angstroms. So those are the same length scale that we are talking about. And then the angstrom is really good for chemists, because if you look at using the length scale angstrom here, it's sort of the integers, right? 1, 2. So the good rule of thumb is carbon-carbon bond is about 1 or 2 angstroms. So this is what you're dealing with. Not 0.1 nanometer, not hundreds of picometers. So that's why the chemists also use a length scale that is an angstrom. At any rate, so this bond supposed to be, if it is a normal 154, but this is a 147, which is a shorter. So that's a 1. And if you're looking at the single bond length with 154 picometer, double bond is 134. So double bond is shorter than single bond. Triple bond even shorter. Okay? So the double bond-like character is a shorter bond. So what this one is saying that is, this single bond, although I draw it as a single bond, it has a nature about double bond characters. Okay? It has a minor taste of the double bond characters. And then how do I give it to you on this? So here, I'm going to actually start from here. When you say sp2, what that means is carbon is made up with sp2 plus p, right? That's an extra orbital they can use. The p orbital looks like this, and it has a plus and minus. It has a polarity in it. And then if you have a 2 sp2, p overlap makes a pi bond. And then I think that you guys have seen that in the lecture that I'm going to draw here. So this sigma bonding shown in the molecule, shown up here, is all like a single bond, but I am going to highlight the pi bonding. which is responsible for this extra line. And the real shape of pi bonding is coming from this overlap, this p orbital overlap. Right? There is another pi bonding, which is real representation is this extra p orbital is going to form this sideways overlap, and it has a polarity. So I'll put this as a plus and this is a minus. So they do have this overlap, and they form this pi bond. But now I'm looking at here, well, what about this? Is it possible for them to have? And the answer is yes. Okay? So for them, it's possible for them to form. Although I draw the molecule double bond, single bond, double bond, so this is their major the bonding. But there's a secondary interaction between carbon 2 and 3 by forming this bond. Okay? So this has a little bit of a nature about the double bond. So therefore, without those sideways overlap, which is an extra rubber band tying the knot, tying the bond these atoms together, you are going to have the 154, but now because of this, the number is 147. So this is answer. So that's a little bit more wordier example on this, and essentially the example I'm showing up here is the region between the carbon 2 and 3, because there's a sideways overlaps. I want to do a little bit extra information too. If I'm just putting it a simple way, let's put this one on this way. Okay, so these are I'm just highlighting the pi bond p orbitals here. So this is one, they can have this, they can have that, and there will be a sideways interactions. Okay. Oh, I think that I made a mistake. So that's what it looks like. But if you're looking at other possibilities, what I'm doing here now is I'm doing polarity. One side is keeping the same, but the other carbon 3 and 4 has a flipped polarity. As far as they are concerned, nothing has changed. Right? But now we are having this, what they call the anti-bonding character. There's a nodal plane where the electrons are not overlapping. Because a pi is a dumbbell-like one, there's a polarity. I can maintain this one to be a double bond, and this pi orientation can cause a sideways overlap, whereas the other arrangement, this cannot have a sideways overlap. And so therefore, this bonding is weaker than the bonding that you saw between 1 and 2 and 3 and 4. So that's another reason that they are different, if you want to know a little bit more detail. And this is what's called the molecular orbital theory that the organic chemist class will cover more details. Okay, any questions? Can I move on?